Hey, it is Mr. Shrum. I am back with another tutorial, and this one's all about motion and how we describe it. So looking at the objective in scientific language, we will identify kinematic quantities that are used to describe motion, distinguishing between scalar and vector quantities. Yeah, and here's the contents of everything. So our introduction tells us that everything in the universe is in motion with respect to something else. So there's always a point of reference in which something is moving. Earth revolves around the sun, and the sun orbits the center of our galaxy, the Milky Way. And the study of motion itself is called kinematics. And it's very key to understanding the entire field of physics. So in physics, motion is defined as a change in the position of a body with respect to a reference point. So in the example, imagine you're sitting in a moving train. With the train as your reference point, a bottle of water held steadily in your hand is static. It is not moving in terms of the train versus the water bottle. But imagine a man standing outside on a road looking at the train passing by. With the solid ground as his reference point, he sees you, the bottle, and the train all traveling at the same speed and in the same direction. So depending from your point of view, something may be moving or not moving. It's all relative. Now imagine cars in different lanes moving along a freeway. So think about 3 cars in motion. One is fast moving in the carpool lane. There's one in the middle lane. And then the third car is the slowest in the slow lane to the right. And it's used to enter or exit the freeway. So we have the fastest, the middle, and the slowest lane. What affects each car's motion? Where will each be after 2 seconds? What factors determine how far each car will travel over time? What type of motion are these cars displaying? Kinematics answers all these types of questions. And this lesson will cover 17th century scientist Galileo Galilei experiments to measure and predict motion. So we're going to study how to describe motion that includes direction, the factors that influence motion, such as friction and different types of motion. And it will also introduce the concept of inertia and how it relates to motion. So now we're going to talk about properties of motion. When you think of motion, what comes to mind? A tennis ball flying across the court. I think of sports like a basketball or a football. Someone doing stunts on a skateboard. Yeah, a skateboarder. Or maybe an amusement park ride, going up, down, forward, and all around. A simple definition of motion is any movement or change in an object's position. For centuries, hundreds of years, philosophers and scientists have tried to understand motion and its properties. Aristotle, a famous Greek philosopher, presented some of the earliest written theories about motion itself. They were accepted from about 500 BC to the early 1600s. But then Italian scientist Galileo Galilei, great name for a scientist, first of all, but he recorded careful observations and experimented with motion. His observations caused him to challenge what Aristotle had proven 2,000 years earlier. Galileo's work marks the beginning of modern science. Yeah, we're stepping into modernity. Sorry about that. Fix the setting. Before getting into what Aristotle thought about motion and how Galileo overturned his theories, we need to explain a few concepts to better understand motion. These concepts include distance, displacement, speed, velocity, and acceleration. So first of all, the two letters are distance, displacement, starting with D, distance and displacement. In physics, distance is the length measured between 2 points. Total distance is the distance measured along a path, no matter how complex that path might be. And that means that distance is a scalar quantity. It just measures magnitude, just a generic numerical value, and it doesn't tell you which way you went. So you say I traveled 60 miles. That doesn't tell you which way you traveled for 60 miles or necessarily that you went in a straight line, right? You could just keep taking turns for 60 miles and wind up not that far away from where you initially started. However, displacement is defined as the shortest path from an initial position to a later position. And that is a vector quantity because that's measuring both magnitude, how far away, and direction. So in reference to something else, where did you travel from? To understand the difference between distance and displacement, think about this example. So in your school, you walk 20 meters north from your first hour class to the physics lab. Once your physics lab is over, you walk another 30 meters east to the cafeteria to have lunch. So you walk 20 meters north, then 30 meters east to have lunch. The total distance you cover is 50 meters. However, that's not the shortest path to the cafeteria from your classroom. The shortest route would be about 36 meters and about 34 degrees north of due east. So that is a measure of your displacement. It specifies both magnitude and direction. We have magnitude, 36 meters, direction, 34 degrees north of due east. Speed, invalid source, interesting. Speed is an object's rate of change of distance over time. So S equals distance, change in distance over time. Imagine a car moving very fast from a stop position. Initially, the speed is 0, but its average speed during the first 3.8 seconds is 4.5 meters per second. So with a little algebra, you can modify the speed equation to solve for distance. Speed times time, speed multiplied by time, that's equals distance. So now we have this video of a car. Initial speed, 0. Instantaneous speed at 3 seconds, 7.2 meters per second. So average speed, it doesn't tell you the whole story. It takes everything in and then just divides by the total time. It starts out at 0, yes. But to reach an average speed of 4.5, it must have gone faster than that for a period of time as well. In fact, after 3 seconds, this car traveled at over 7 meters per second. A car's speedometer shows instantaneous speed, and instantaneous means at that exact instant in time. Yeah, and that's typically what you're interested in when you're driving. On the other hand, if you want to know how fast we traveled overall during a long road trip, you would calculate average speed. So the total distance divided by the total time. Speed, like distance, is a scalar quantity. Since you're just dividing distance by time, a scalar by scalar, you're still getting a scalar quantity. And no direction is still involved. However, velocity is different from speed because it specifies a direction in addition to speed. So it's telling you how fast you're going and where, in what direction. So in an example, a bus moves to the east 20 meters per second. In the evening, from the same starting point, the bus moves 20 meters per second to the west. So we're going 20 meters per second to the east, and then 20 meters per second to the west. So velocity in the morning, you can write that as 20 meters per second toward the east, and then in the evening, same thing, but toward the west. So this example tells us that velocity is the speed of an object, the bus, and the direction in which the object changes its position. So to calculate velocity, we consider displacement and not only distance, because displacement is the change in the position of an object. Velocity is defined as the displacement of an object over time. In our bus example, if east is the positive direction, right? Because we're going to the, kind of like a number line, then the velocity in the morning is positive 20 meters per second. But if we consider the left decreasing in like the number line value, the velocity is negative 20 meters per second. So sorry, positive and negative is a way for us to tell more information about the number. So if it was just 20 meters per second, that would be speed. But since we have plus and minus, that tells you the direction of the speed as well. Acceleration is a step further. It tells you even more information. When an object's velocity changes, its speed, direction, or both speed and direction change. So a change in velocity over a period of time is acceleration. Acceleration tells you how fast the velocity is changing over a period of time. So velocity and acceleration are vector quantities. And to calculate acceleration, you're dividing the change in time, you're dividing the change in velocity by the change in time. So we have velocity change divided by time change. So for example, a car starts at rest, so we have 0 meters per second, and accelerates at a nearly constant rate for 3 seconds. At 3 seconds, It has a velocity of positive 7.2 meters per second, and that means to the east. What is its average acceleration? So its average acceleration is 7.2 meters per second. We're given that velocity at 3 seconds. And then we divide by 3 seconds to get positive 2.4 meters per second squared. So these are the units we use when we're talking about acceleration. Meters divided by seconds is meters over seconds squared. The change in velocity here is toward the east, the positive direction. The acceleration then is a positive velocity change divided by a positive time change. Acceleration here must be positive because you're accelerating toward the east, which is the positive direction from our point of view. So we have distance, scalar quantity, displacement, velocity, acceleration. Okay? Distance and speed, scalar, displacement, velocity, acceleration, vectors. So now that you've studied very basic measures of motion, let's see what Aristotle and Galileo had to say about an object's motion. Aristotle, according to him, the speed at which an object falls is directly proportional to the object's mass. So, for example, a 1 kilogram rock falls to the ground 1,000,000 times faster than a 100 milligram feather. He also claimed that the object's speed was inversely proportional to the density of the medium it was falling through. For example, an object falling through air falls faster than an object falling through water. Aristotle put forward these two theories, believing that an object is always subject to the influence of some medium, such as air or water. According to Aristotle, a vacuum, a void without matter, that's what that means, couldn't exist. So, with these two theories, that an object is always subject to the influence of submediums such as air or water, a vacuum couldn't exist. His theories reflected everyday experience and sort of a common sense logic to it. Like there's some intuition involved. Most people believe, studied, and taught until Galileo's motion experiments proved differently. This is what people thought for a very long time. They just kind of assumed that this is the way things worked when it came to motion until Galileo, good old Galileo. His education included studying Aristotle's theories of motion, but with his own experiments and observations, he began to question whether those were actually legitimate claims or not. Galileo described dropping objects of different weights from the top of the Leaning Tower of Pisa in Italy. His observations led him to realize that objects of different weights dropped simultaneously landed on the ground with just a slight difference in time. Based on this information, Galileo refuted Aristotle's theory that a stone double the weight of another stone would hit the ground sooner. But when a feather and a rock are dropped from the same height at the same time, doesn't the rock hit the ground first? Yes, but that's due to air resistance, not the weight of the object itself. In a vacuum, where they suck out all of the air, the feather and the rock would hit the ground at the same time. Whether in the lab or on the moon, you can observe what happens when a rock and feather are dropped in a vacuum. And we'll do that right here. This is on NASA's site. Apollo 15 hammer feather drop. Can you all see that? So in one hand he has the hammer, in the other he has a feather. And in this situation, unlike Earth, where we have lots of air that can resist the feather from hitting the ground, Commander David Scott performed this live demonstration on the Apollo 15 moonwalk. So the moon acts sort of like a vacuum. Strange, very strange. It feels otherworldly to us because that's not how most of us encounter day-to-day life. So seeing something like that is always a little strange. It goes against what I, in my human mind, would expect. Now we're going to talk about the types of motion. 3 types we're going to talk about: translation, rotation, and vibration. Translation is one motion in which you're going from one point to another. It's like the most basic motion, and I think what most people believe or they see in their mind when you say motion. It's just something going from one point to another point. There are 2 types: linear motion, where it moves in a straight line, or curvilinear, which is something that's not linear, a little curvy. So think about cars on the freeway. If the road is straight, the cars are displaying linear motion. But when the road curves, the cars go along each curve in curvilinear motion. See? So these guys are going straight, linear motion, and these are about to turn. So curvilinear. Rotation is exactly what you think it is when an object spins around an axis without altering its position in space. It's rotating. So think of when you spin a top, or you see an ice skater or a ballerina spinning in place, or even the Earth rotating around its axis. That is rotation. So we have translation, rotation, and then vibration. Take a rubber band, stretch it across 2 fingers, pluck it, and it'll vibrate back and forth super quickly. Your cell phone probably has a vibrate setting. I know I use mine all the time. And it makes the phone vibrate when someone calls. Instruments with strings, such as guitar, violin, cello, mandolin, banjo, bass, all types of instruments with strings, they display vibrational motion to create music. As you pluck a string, it vibrates and reverberates, and that moves the the particles around it and creates sound waves. And then it hits your eardrum, the little bones in your ear, it vibrates those, and then you can hear music. Very awesome. Sometimes an object may display more than one kind of motion at the same time. So a car's tires display linear motion as they go forward, but also rotational motion because they're spinning around on the axle. And an example here is you can see all three types of motion at an amusement park. And we'll take a look at those in the next slide. So we have the giant swing. A giant swing goes back and forth. It'll swing in this big motion. On an axis, it displays a periodic or vibrational motion. A roller coaster, I think probably my favorite amusement ride. It's, yeah, the most popular of all park rides. Curves, loops, dips. It's an example of translational motion, specifically curvilinear. And the people on the ride go from one point to another in a curved, loopy path. Water slide, another fun ride. If it's a loopy water slide and it goes around these curves, then that's curvilinear, translational motion. But if it's more of one of those very long, straight slides, then that could be linear motion. The tower drop. So this one is where they raise you up very, very high and then suddenly drops you. It goes up in a straight line. So that can be translational, linear, translational. And then it also displays vibrational motion, where the people on the ride are suspended in midair while their seats vibrate forcefully, adding to the thrill. This makes me want to go to the fair. The Ferris wheel, another iconic amusement park ride. It rotates around this axis here. So that's all rotational motion. And the same thing with the carousel. It's like the Ferris wheel, but on its side. Carousel or merry-go-round rotates on an axis. So that is rotational. So we have rotational, translational, and vibrational. Translational, curvilinear, translational. And then we have vibrational. Yeah, good stuff. So we are given a matching exercise. Propeller of an aircraft, rotational, because it's spinning around on an axis. A car driving up a winding mountain road. Winding sounds curvy, and it's going from one point to another. That's curvilinear. Music being played on a stringed instrument. Gotta vibrate those springs. Strings, not springs. What am I saying? And then runners sprinting across a straight track is a linear. Ta-da. Inertia. Here is a statue of Aristotle, a bust. Not a bust, it's a whole body. In everyday use, inertia means the tendency to stay still or to not get anything done. So when you think of something that's inert, it doesn't really move or act. This everyday understanding of inertia is more than 2,500 years old, and it can be traced back to the ancient Greeks. Aristotle believed that a force needed to be constantly applied to an object to keep it moving. Otherwise, it would stop. In his day, it was obvious that something, such as a donkey, was needed to pull a cart. If the donkey stopped, the cart stopped as well. However, there were objects that were apparently able to move without constantly being pushed. An arrow, for example, can fly for a great distance without a constant push. And he hypothesized that the bow provides the initial push to the arrow, but that it is also up it sets up a wind that continues to push the arrow through the air over a great distance. Yeah, so this Aristotle guy, he had a logic to his thoughts. It just turned out that it's not that way at all. So, one of Galileo's most important discoveries was that Aristotle's common sense understanding of motion and inertia was just wrong. Galileo concluded that an object opposes any change to its state of motion. So if an object is standing still, it will oppose being moved. If it's moving, however, it will oppose any change to its movement. So an object in motion will continue to travel in a straight line at a constant velocity unless it's acted upon by some outside force. This is the law of inertia, and it became the basis for Isaac Newton's first law of motion. The understanding that we don't need to constantly push objects to keep them moving was an important scientific breakthrough. It allowed Newton to understand the relationship between force and motion and to extend the laws of physics from Earth and the sun to planets and stars. So let's see how Galileo came to this revolutionary understanding of how the world works. He was the first scientist to study motion of a pendulum, a mass suspended by a string, and he discovered that a pendulum is a good timekeeper. It swings back and forth at a constant rate that depends only on the length of the string. The amount of mass, for example, doesn't matter. At that time, a more accurate and more dependable clock was highly coveted and therefore valuable. So he was really interested in this property of timekeeping. Pendulum clocks were a result of Galileo's discovery. So that's cool. But he also noticed that a pendulum swings back and forth for a long time without losing much height. So it would swing and reach the same height for quite a long period of time. If started at a given height on one side, it would swing to the other side to almost the same height. He found that this was true even if he stuck a peg in the path of the string. The pendulum bob would still swing to the same height on the other side, even though there was a peg. So the findings started getting his brain thinking that Aristotle was probably not correct. Poor Aristotle. To understand his findings about inertia further, he used balls and rolled them down the sides of bowls and ramps. And just as with the pendulum, he found that he could roll a ball down one ramp and then up another to the same height. No matter whether the angle of the second ramp was steep or gradual, the ball would roll up close to the same height it started from. So he wondered, what happens if the second ramp never goes up at all, if it was just flat? His conclusion was that the ball would continue to roll in a straight line at a constant speed forever. Galileo had found an entirely new way to understand inertia. But still, in our everyday life, objects do slow down and stop. And how did Galileo address that at all? So, with his new understanding of motion as an ideal, meaning in a perfect world, Galileo realized that some systems, such as pendulum, took a very long time to slow down and stop. Others, such as a donkey and cart, stopped almost immediately. So he noticed that these situations were different. The mud of the road and the wood on wood rubbing of the cart provided forces that would oppose the motion of the cart. The only force that would slow down the pendulum was the thin air it swung through. So forces, and especially what we know now is friction, cause objects to slow down and stop. Without external forces, such as friction, objects would continue to move at a constant velocity, a constant speed in a straight line. So, in a vacuum, without other things entering the system, this is how objects initially want to behave. And we experience inertia every day. Imagine that you're standing in a moving bus and the driver hits the brakes suddenly. If you're caught by surprise, you may move forward. While the bus was moving, your body traveled forward with the bus. But when the bus suddenly stopped, you continued moving the way you were moving before. Later on, at the bus stop, the bus is standing still and then the driver hits the accelerator. In this case, you seem to lurch backwards. Your body is at rest, and then the bus starts to move, and then your body wants to stay where it was. But now you're on a moving bus again. So you feel the results of inertia when a vehicle changes its direction of motion. If you're riding in a car and it makes a sharp turn to the right, your body seems to sway to the left. And actually, your body is trying to follow the original straight line path that you were initially going. The car and seatbelt pull you to the right, but the top of your body continues its previous motion. So it seems like you're going to the left. It's all inertia. So going back to the freeway, consider that there's an accident. External forces act on the car involved in the crash and change their motion. So if a car is hit from behind, its motion will change and it will propel forward rapidly. Or maybe a driver loses control and crashes into a road divider. The divider exerts an external force that acts on the motion of the car to bring it to a sudden stop. Because of inertia, the driver could be thrown against the windshield and seriously injured. So, seatbelts and airbags are designed with inertia in mind. So, if there's a sudden stop, both the seatbelt and the airbag can spread the force to stop the driver's body over a wide area and over a longer time. And this cushions the impact. So this is all designed with inertia in mind. Here we have a little lesson activity. It gives you instructions. Go to your backyard or your local basketball court, tennis court, and see if you can predict the motion and inertia accurately. And you can bring a friend, classmate, and a ball. And it involves sprinting and jogging and walking. So that is a good workout, actually. I encourage you to go try that. Which statement best defines inertia? So which one sounds most correct to you? An object's motion is unaffected by any external forces acting upon it? Not necessarily. An object responds to a force by tending to move in the direction of that force? No. An object opposes any motion, naturally returning to a state of rest on its own. An object opposes any change in its velocity, either to its direction or to its speed. The last one is the correct. Inertia is the property of an object that opposes any change to its velocity. So it doesn't want to change direction or speed. It resists. And that brings us to the summary. Motion. It's fundamental to the study of mechanics and to physics in general. To understand motion, it's important to understand distance, displacement, speed, velocity, and acceleration, and how they are interrelated. Galileo, the Italian scientist, performed various experiments that laid the groundwork for how we understand motion today. The three basic types of motion are translation, rotation, and vibration. An object in motion can display one or more types of motion all at the same time. A bicycle is a good example. The tires are rotating, exhibiting rotational motion, and the bike can go in a linear direction or a curvilinear translational motion is being used for that. Inertia is an object's resistance to any change in its velocity. And you can find this in various day-to-day phenomena, such as when you're riding in vehicles, riding a bus, pretty much anything where you're in something that's moving and you're not. You can experience the changes in direction and speed and how your body doesn't initially want to do it. But that brings us to the end of describing motion. I hope you found that informative and helpful, and I will see you guys later. Bye, everybody.